Hello all, welcome to this video on System Software Lab. Today I'll be talking about macroprocessor and its implementation in C. Let us begin by looking into what a macroprocessor is. An assembly language macro is a template whose format represents a pattern of 0 or more assembly language statements that might be common to multiple programs. For this purpose, a macro language is used to provide a syntax for defining macros, where a sequence of assembly language statements can be represented by a macro. A macro call is inserted into the assembly program source code, where the assembly code would otherwise go. A macro facility is used to interpret macro definition and expand each macro call as it occurs with the requisite pattern of assembly language statements, providing expanded source code ready for the assembler. Hence, the macro facility is a preprocessor which interprets all macro calls into assembly code prior to passing the expanded code onto the assembler. The macro preprocessor included with C compilers with calls such as #include uses the same idea even though the assembly language macro facilities predate the similar compiler preprocessors. A macro processor is not directly related to the architecture of the computer on which it is run. They can be used with high-level programming languages, OS command languages, etc. Now we'll look into the history of macroprocessors. Macro languages were invented early in the history of computing. In the 1950s, Alan Perlis suggested that the macro language be independent of the language being processed. Techniques such as conditional and recursive macros and using macros to define other macros were described by Douglas McElroy of Bell Labs in the 1960s. GPM, or the General Purpose Macro Generator, was developed at the University of Cambridge, UK in the mid-1960s under the direction of Christopher Strachey. Now GPM fit into 250 machine instructions. Inspired by GPM, while visiting Strachey's lab in 1968, McElroy wrote a model preprocessor that fit into a page of Snowball 3 code, and McElroy and Robert Morris developed a series of further models at Bell Labs. One particularly important general purpose macroprocessor in the 60s was ML1 or Macro Language 1, developed as part of PhD research by a Cambridge postgraduate named Peter J. Brown. Now, ML1 operates on a character stream and requires no special format for its input nor any special flag characters to introduce macros. Douglas McElroy, Robert Morris, and Andrew Hall at AT&T Bell Labs followed up with M6, a general-purpose macro processor used to port the Fortran source code of the Altran computer algebra system. It was influenced by GPM and TRAC. M6 source code consisted of about 600 Fortran statements. Brian Kernighan and P.J. Plogger implemented a Unix macro processor language which inspired Dennis Ritchie to write M3, a macro processor for the AP3 mini computer. Kernighan and Ritchie then joined forces to develop the original M4 in the 1970s. It had only 21 built-in macros. Professor A. Dane Samples described and implemented a further evolution in the form of M5 in the 1990s. Now let us look into the basic macro processor functions. We'll begin with macro definition. Assembly language macro definitions can be predefined and placed in a macro library or can be included in line with the assembly language program. The handling sequence for the program looks like this. Now in the beginning, we'll have an assembly source code with macro definition and calls in it, which is sent to a macro facility which is connected to the macro library where we have the macro definition. and other details related to the macros. Now, after the expanded source code is generated, it is sent to the assembler, which will convert it into object code. Now, that is given to the linkage editor, which is connected to other modules in the program, and all these modules will be linked together and a load module will be created. This is sent to the loader, which will execute the module. Now we'll look into the macro definition format. First, we have the prototype statement where we have the macro name followed by the acronym macro, followed by the list of parameters which begin by an ampersand and separated by comma. Then we have the body of the macro, and finally the end statement, which is MEND, which marks the end of the macro. Now this is an example of a program where we have a macro definition. Now the name of the macro here is rdbuff macro, and the parameter list, which is starting with an ampersand followed by the comma. Then we have the definition of the macro, and finally MEND, which marks the end of the macro. Then we have the main program. Note that the program is of the format label, opcode and operand. So this will be the order in which data will be taken when we execute the program for macro processor. So here C loop is a label, rdbuff is the macro, and this is the statement where we call the macro, and these are the arguments to be passed into it. Two assembler directives, macro and MEND, are used in macro definitions. First, macro statements identify the beginning of a macro definition. Now the symbol in the label field, which is rdbuff, is the name of the macro, and entries in the operand field identify the parameters of the macro instruction. Each parameter begins with an ampersand, which facilitates the substitution of parameters during macro expansion. Now the macro name and parameters define a pattern or prototype for the macro instruction used by the programmer. Following the macro directive are the statements that make up the body of the macro definition. The MEND assembler directive marks the end of the macro definition. Macro invocation or macro call statement gives the name of the macro instruction being invoked and the arguments to be used in expanding the macro. Now we look into keyword and positional parameters. Now the prototype statements parameter list as given to this point uses what is known as positional parameters. The position of a parameter in the comma separated list determines which entry it represents. Note that two successive commas in the list represent an omitted parameter. A keyword parameter is one specified in the comma separated list by the form ampersand equal to. Now each of the macro invocation statement has been expanded into the statements that form the body of the macro with the arguments from the macro invocation substituted for the parameters in the macro prototype. Now the arguments and parameters are associated with one another according to their positions. The first argument in the macro invocation corresponds to the first parameter in the macro prototype, and so on. Now here the label on the macro invocation statement, which is C loop, has been retained as a label on the first statement generated in the macro expansion. This allows the programmer to use the macro instruction in exactly the same way as an assembler language mnemonic. After macro processing, the expanded file can be used as input to the assembler. Now the macro invocation statements will be treated as comments here, and the statements generated from the macro expansion will be assembled exactly as though they had been written directly by the programmer. The statements that form the expansion of a macro are generated and assembled each time the macro is invoked. Now we look into macroprocessor algorithm, and data structures. It is easy to design a two-pass macroprocessor in which all the macro definitions are processed during the first pass and all macro invocation statements are expanded during the second pass. However, such a two-pass macroprocessor would not allow the body of one macro instruction to contain definitions of other macros because all macros would have to be defined during the first pass before any macro invocation are expanded. Now, these are two macros written for SIC and SIC-XE. One is macro S and the other is macro X. Now the body of the first macro, macro S, contains statements that define RDBuf and other macro instructions for an SIC system, which is the standard version. The body of the second macro instruction, macro X, define these same macros for the SIC-XE system. A program that is to be run on a standard SIC system could invoke macro S to define the other utility macro instructions. A program for an SIC-XE system could invoke macro X to define these same macros in their XE version. In this way, the same program could run on either a standard SIC machine or an SIC-XE machine. The only change required would be the invocation of either macro S or macro X. It is important to understand that defining macro S or macro X does not define RDBuf and the other macro instructions. These definitions are processed only when an invocation of macro S or macro X is expanded. A one-pass macro processor that can alternate between macro definition and macro expansion is able to handle macros like these. Because of the one-pass structure, the definition of a macro must appear in the source program before any statements that invoke that macro. There are three main data structures involved in macro processor. The macro definitions are stored in a definition table or def tab, which contains the macro prototype and statements that make up the macro body with a few modifications. Command lines from the macro definition are not entered into the def tab because they will not be part of the macro expansion. References to the macro instruction parameters are converted into positional notation for efficiency in substituting arguments. The macro names are also entered into num tab or name table, which serves as an index to def tab. For each macro instruction defined, num tab contains pointers to the beginning and end of the definition in def tab. The third data structure is an argument table or arg tab, which is used during the expansion of macro invocation. When a macro invocation statement is recognized, the arguments are stored in arg tab according to their position in the argument list. As the macro is expanded, the arguments from arg tab are substituted for the corresponding parameters in macro body. Now this is an illustration of num tab, arg tab and def tab. Now this is the definition of the macro, and this is the name of the macro and pointers to the beginning and end of the macro, and arg tab contains the arguments, which can be seen in the macro invocation statement. Now the parameter ampersand in device has been converted to $1, indicating that it is the first parameter in the prototype. Now that can be seen here. Now in the code we have TD, corresponding argument is indef, which has been replaced with $1, and ampersand buffered has been converted to $2, as it can be seen here. The second argument was ampersand buffered, which is converted to $2, and so on. Now when a $n notation is recognized in a line from def tab, a symbol indexing operation supplies the proper argument from arg tab. Now we'll look into the macro processor algorithm. before seeing the actual algorithm, we'll discuss some of the procedures that can be found in the algorithm. First one is get line. Now get line is used for checking if the macro processor is in expanding mode or not. If it is in expanding mode, then it gets the definition from def tab and arguments from arg tab. If it's not in the expanding mode, then it reads the next input line. Next procedure is a process line, which checks the num tab for opcode. If the opcode is found, then it calls the expand procedure. Now, if the opcode is a macro, then it will call the define procedure, else it will write that line into the expanded file. Now, another procedure is define. Now, that enters the macro name into num tab and prototype to def tab. It also sets the level as 1. Now, until the level is greater than 0, it will substitute the positional notations for the parameters, thus entering the line to def tab. Now, if the opcode is a macro, then level is incremented by 1. If the opcode is mend, level is decremented by 1, and it stores the pointers to beginning and end of the definition in num tab. Then we have the expand procedure, which will set the macro processor into the expanding mode. It gets the macro prototype from the def tab. It sets up the arguments from arg tab and writes the macro invocation to the file as a command. Finally, it will turn off the expanding mode of the macro processor. Now, this is the actual algorithm of macro processor. Now the procedure define, which is called when the beginning of a macro definition is recognized, makes the appropriate entries into def tab and num tab. Expand is called to set up the argument values in arg tab and expand a macro invocation statement. The procedure getLine, which is used at several points in the algorithm, gets the next line to be processed. This line may come from def tab, that is the next line of a macro being expanded, or from the input file depending upon whether the Boolean variable expanding is set to true or false. The handling of macro definitions within macros will be seen next. When a macro definition is being entered into def tab, the normal approach would be to continue until a mend directive is reached. The mend in code would be taken as the end of the definition of the macro. To solve this problem, our define procedure maintains a counter named level. Each time a macro directive is read, the value of level is increased by 1. Each time a mend directive is read, the value of level is decreased by 1. When the level reaches 0, the mend that corresponds to the original macro directive has been found. Now this process is very much like matching the left and right parentheses when scanning an arithmetic expression. Most macro processors allow the definitions of commonly used macro instructions to appear in a standard system library rather than in the source program. This makes the use of such macros much more convenient. Definitions are retrieved from this library as they are needed during macro processing. Now we look into the macro processor program logic. Now all these files like the input num tab, def tab, arg tab, and even the output file has pointers pointed to it. Now first of all, we set the file pointers. Now for the input, the file pointer is in read mode, and for the output it is in write mode. For all the rest, it will be in both read and write mode. Then we read the lines from the input file, which will be in the format label, mnemonic, and operand. Now until the opcode is not end, it checks if the opcode is meant. Now until the opcode is a macro, then we'll take the macro name, add it into num tab. We take the macro prototype and add it into the def tab. Then we read the next line of code and check If at all it is not meant, and if checks if the operand begins with an ampersand, it will replace the parameters with the positional notations. For example, question mark 1, question mark 2, etc. And it will write the macro definition to def tab. Now all these will repeat until it's not meant. It's a loop going on here. Then what they do next is checking if the opcode is not a macro. Then what it does is it will read the macro name from the num tab, and it will check if that name in the num tab and the name of the macro, that is the statement of macro call we came across in the program, if those two names match or not. If they don't match, it means the macro definition is not available. Otherwise, what it does is it will take the length of the operand that is following the name of the macro in macro call, takes the length, separates out the arguments and fill it into the arg tab, and it enters this macro call statement as a commented macro invocation statement into the file, and it reads the next line of macro definition. Now until the mnemonic is not meant, it will keep on reading lines of def tab. Now it checks if the operand starts with a question mark or not. That means it is the positional notation we gave before. There we give the arguments from the arg tab. We replace their names. And finally, the end of the program is reached, which is written to the output file, and all the pointers are closed. Now this is the program of macro processor. Now this is the input program given to the macro processor. Now this is the name of the macro and the arguments. This is the definition, ends with meant. Now this is the macro call, which has arguments n1 and n2. Now the output here will have these following files. Now this is the output file where we have expanded the macro. We have replaced the definition with the statements inside it, and we have added the invocation line as a comment here, and we have replaced the arguments. Then we have the arg tab where we have the arguments n1, n2, which was present in the macro call. Then there is num tab where we have the name of the macro. Then there is def tab, which contains the definition of the macro from the program. And this is the output that is displayed in the terminal, that is explaining how the program is exactly working. So the first statement in the program was sample start 1000, which is not to be processed by the macro processor. So we define it as the line from input code. Then we came across the macro definition. So we write it as inside macro. We are entering the macro prototype to def tab and the macro definition lines into def tab, and finally we reached the meant. Then the next line was the macro call. So since it's a call, we are adding it as a commented macro invocation statement to the output file, and we also replace the arguments in the input, that is n1 and n2. Then the next two lines are for reserve word, that is also not processed by the macro processor, so they are written as such. And finally end, which marks the end of the program, which is also not processed. Now we'll look into a demo of this program. So here you can see there is one pass macro and the input. One pass macro is the program whose logic I explained before, and we have the input file. We go to the terminal and compile the program. Since there are no compilation errors, we run the program. Now the output in the terminal is the one that I explained before, and we have 4 files created: num tab with the name of the macro, def tab with the definition of the macro, then arg tab with the name of the arguments, and finally the output file where the expanded source code is written. That's all for now. Thank you for watching.